Yes, so we have about 3 minutes, right? Wait for about 3 more minutes before we start the first session. I think, yeah, I hope everyone not too exhausted about yesterday's trip, and very good. Thank you very much, Professor, for Kumar, for arrangement and everything. Very enjoyable. And I think this session actually on your schedule is the same. From the two sessions are the same, but it's actually not the same. We are talking about this topic first before talking about a specific example on the nickel-based superalloy non-homogeneity in microstructure prediction. So wait for a few more minutes before we start, and I probably repeat again. Standing here. Standing here. Is that in the frame, right? Okay. Yes. Okay. I think we can leave it until question answer session, or because I think how say another slide is very metallurgy actually. I think I may need spend some time, or I will be very quick, so we have some long time for discussion. Yes, so I think it's about the time to start. So just let you know, on your schedule you have a similar topic for this two morning session, but it's actually there are difference, because the intention of this is to end we approaching to the end of this short course now. So before we going to last two topic, which is about physics-based simulation for one of the defects we call non-homogeneity in additive. In the next session, we want to give you overview about all the defect which is formed in additive. And the last one will be the example, next session about physics-based, and the session after, which is tomorrow morning, will be about how can we use data-driven or machine learning to come up with a new alloy which we design. Just a success case that we did in the past many years on nickel-based superalloy. So it will heavily focus on that kind of material that I'm working on. So today is about defect formation and defect type in additive manufacturing. As you may know, defects is always the problem for engineer, metallurgy, and everyone. No one want to get defect, right, on your printed part. But unfortunately, the nature is not that simple. You need to deal with somehow, and most importantly, as an engineer or scientist, we need to understand why it's happened and how can we avoid that if at all possible. So as you know, this is our very first slide I present to you at the beginning, that we know now about the processing, microstructure, and mechanical property, and defect which present can happen across these entire PSP, actually we call property structure, processing structure property pathway that we are going through. This is smaller scale. This is bigger, so this is a crack across the build, which we will talk more and more in the slide. And then you see when we do the EBSD map here, you see the strain which is not homogeneous, non-homogeneous anymore. And this is what we found after we do some atom probe tomography. But anyway, this is the defects thing that we are trying to talk today. So just to remind again, in order to successfully print something in additive, as you know, we understand from the, I think, from the loose cause of that at the laser matter interaction with the defect. This is doing processing, not solidified yet. And then you see a lot of things going on here. I think probably I try to bring you to the chart that will see easily what happened here. It's so dynamic. You see the plume that's coming out here and sometimes sputter and whatsoever. How can we predict that? That is one other question. And this one is probably quite, again, this is flashing the similar manner. You see some plume coming out as well, but probably not as strong as in this case. And this is bigger, length scale. And the defects here as well in powder-bed fusion, as I mentioned several times before, is a porosity, a subsurface porosity, and then you will get surface roughness. And then hence another thing is this distortion. It's a closed-form processing structure, and finally a property type of defect which you may see in it, commonly in additive manufacturing. So the question is, how can we may systematically classify this defect and try to understand in the single, common language for defects. So there is a good paper that they try to review what actually multi-scale defect in powder-bed fusion additively manufacture metal and alloy. So this is a classification of multi-scale defect in powder-bed fusion, LPBF, if you like. It doesn't need to be LPBF. It can be electron beam powder bed as well. So you will see from here that they classify into three categories. One is actually related to geometry, which is a path distortion. So this is a classic kind of, what is this called? Oh, I just forgot all in sudden, but it's a kind of, yes, cantilever, but yes, with this kind of feature. So it's actually similar if you know on, a case study of AM bench at a NIST National Lab. This will be a bridge over this with different, size of the fin here. So the lamination also geometry related, but geometry related is basically because the distortion or residual stress build up in the part. And another defect type is actually surface integrity related. So it's kind of staircase effect based on the, it's probably somehow based on the geometry as well, but they focus more on the surface level, which is layer thickness. Or sometimes due to the melting, you get partially melted particle or powder. And then as a melting progress, as we discussed briefly in the previous few sessions, you'll get a balling effect, which is on the surface tension kind of phenomenon. That pretty much related to during melting or I would say the thermofluid interaction that we're talking about. And this is surface cracking. This is one of our work that published in ACTA 2021. And this is the same from the same work here. So we talk about hot cracking. So you will I will tell you a little bit more about these cases that cracking is not just here as a microstructure defect due to the, and I mean porosity also classified in number of ways. You may know lack of fusion, voids, process-induced porosity, and also, I mean, coming from process-induced, and also the the pore trap during the powder production, something like that. And the texture and columnar grains, I mean, they define columnar grains as the defects or the textured material is not preferred in the process. And also, last but not least, this is something I will give example next lecture, which is a compositional defect. What is this? And then this location defect that actually we call cellular structure in additive manufacturing. So I hope this will try to summarize what we discussed in the past few days as well. So this is the geometry-related defect. I mean, give you more detail or example here. Like this is the bridges structure here at the number 1, 2, 3, 4, and then you see some bending of the part as a function of probably here. If you see closely, there will be different in terms of the size of the small part here. And then there is some delamination, as if you remember one of simulation that we do. If you print something long enough, that you will introduce some intrinsic heat treatment below, and then that means you allow some secondary phase to grow. And that concentration may lead to delamination sometime because it's actually the stress is not continuous throughout the sample. And again, this may relate it as well to the distortion. And this is a bigger part that may induce the geometry-related defect. So people are trying to, correct or study or systematic investigation about feature of the thickness contribute to the geometrical error that I show you example in the last two slides, that they compare between CAD model and the printed model and try to see what is the mismatch. And then you see the error is actually quite significant. It can be up to 35% mismatch or deviate from the geometry that we want to print. And this contribute to the definitely, as I said, if you print something quite long compared with the base material here, you get some bended, or you can measure the stress and also try to predict it. And this is related geometry defect that I tried to say before. Secondly, is about surface or integrity defects here. I mean, this is a staircase effect when you print something in, this is related to layer thickness, as mentioned before. This may be something not making your surface not very smooth, so it's about stepwise, something like that. That is probably pose some challenge in the property that later we're going to use this part. Surface roughness is another problem. Again, this is happening during melting, during printing. Actually, the surface roughness here, as you may know, this may contribute from the quality of the powder as well as the way you print it in terms of the optimized process condition that you choose, laser scan speed, and the power that you use for this process. And definitely partially melted particle or powder is also another defect which may pose some challenge. And then later this may form a porosity. And this one, again, all these three, and actually almost everything here is originated during the laser matter interaction. And you see the balling effect is about the poor wettability related to surface tension and probably viscosity of the metal at the liquid stage that you print. And this is try to summarize, but it's not very inclusive like my previous diagram. And definitely this will be another challenge that in terms of surface integrity, it's not just porosity, but the cracking at different location here. So at the edge, it is due to the rapid cooling, which is different from in the bulk. So this sample we do only 10 millimeter thick. It's not very big anyway, but there's still some micro crack and then macro cracking here. And that, I think this is, I can say to you now, is related to the scanning pattern we use, because at the edge and in the middle we change the way we print it. So that is something to improve. But I think the point here that I will show later is actually related to the composition of the material that probably related to this effect as well. So there will be a surface cracking that connect from the bulk and the surface, and you will see the microstructure in the middle and at the edge are different, looking like this is actually faster, or the growth rate here is more epitaxial or a columnar grain, which we will talk a little bit more later. So this is surface integrity defect. So in terms of microstructure defect, so there are so many microstructure that link to composition, link to the processing as well. But again, this is the internal crack. So basically, this is solid mechanics kind of effect that you see solidification cracking. Why we say solidification cracking? Because it's evident of the small dendrite. Let be aware that this scale is just half micron. So it's so thin that probably you not notice as a dendrite. It's only primary arms that actually taking place here. So you evident at the crack feature here, and then you zoom in using very high resolution SEM, you will see this kind of dendritic structure here. But it's not just the solidification cracking. As I said, there will be another type like briquation cracking, and then carbide cracking as well. So yeah, this is something we want to talk more in detail. And then porosity, again, they classify as internal crack, that probably this porosity act as a stress concentrator, and then this one will actually induce some plasticity in this zone, and then try to crack penetration will be promoted here. And then that, again, this is another scale of the cracking of solidification, and in the Melpool scale. Another defect is about porosity. It is related to the laser matter interaction. I think this basically, I think the first part of today's lecture, just to summarize everything, and then we basically try to predict defect in summary. Actually, so this is a porosity that, this is the material of Invar, which is iron nickel alloy. You will see this one for aerospace application here. You see the way they melt that leads to the doublet splatter and induce some porosity inside, from this synchrotron imaging here. But another, in terms of microstructure defect for porosity, as industrial or engineer, we also want to understand these as a function of process condition. So from the low energy density, intermediate energy density, or high energy density, you will see there is, from this XCT, which is X-ray, micro CT, micro X-ray thermography here, yeah, you will see this is more lack of fusion feature. I will talk to you more in one example of how they classify the defect during the printing in more systematic way using data-driven as well in this slide. next topic. You see, this is lack of fusion, but this is more like process-induced porosity. It's more spherical, rounded. And if you choose the process parameter correctly, this will be a kind of minimum defect that you will see and form. And then that's why normally PV, which is power and velocity, and you can identify some keyhole, probably this related to keyhole porosity, this related to lack of fusion porosity, and this is somewhere in the middle. A boiling effect when you have very high velocity and high power, and then that boiling effect taking place. Again, the boiling, we put it in the last slide on surface integrity. But anyway, it is related to this P and V. Everything originated from here. So next one is the microstructure defect, which is texture columnar grains. It's one of the microstructure defect. So you will see this diagram clearly when you use P and V here. You will see the microstructure change quite significantly. As some condition, let's compare here and here. You will see they are so different in microstructure. And this also contribute to the different scanning pattern that you use as well. If you use only X scan here, you get this microstructure. But if you use X and Y, kind of alternated layer, X, Y, X, Y, this will lead to different, more probably not preferable microstructure you want. We want more equax, more small round shaped microstructure that we need. So as I said to you, this is related to simply thermal model as well. If we try to do something, yeah, you see, if you scan like this, microstructure will grow this way, so we can control the directional growth of the material. But if you scan like this, the microstructure may start to bend it a little bit. But if your scan direction make this melt pool very, hemisphere kind of things, the grain will grow in this direction. That's how you see some feature like this in the melt pool, for example. So we will talk a little bit more as well. I think this one is probably not talking a lot this day, but people start to study, which is a compositional defect. So what I meant by that is actually you may get some segregation, probably heavily during the printing process, and this is not easily detected, and also need advanced characterization to looking at that. This is a cellular structure of LPBF, stainless steel 316L. So it is a commonly used steel for 3D printing. And you see the suggested microsegregation. In overlap to the dislocation cell. So sorry, this will go deep into metallurgy, but it's quite interesting science that we can looking at grain boundary. This actually decorated at that location. And this is because of the formation of dislocation cell at the condition. This is trying to calculate this at the condition of selective of LPBF and the direct energy deposition in the one-dimensional, two-dimensional, and three-dimensional structure here. And you will see some characteristic of DD, 3D, DD, and LPBF are a bit different due to the LPBF quite scanned in a very small, precise region, rather than DD, large melt pool. Or even LPBF, laser, and EBPBF, which is electron beam, you will get different dislocation cell or microstructure as well. So we haven't touched much onto that, but this is, I think, is to metallurgy now, but I just want to mention about this. So how can we detect and also predict it? This is another question that is about the talk for today. So the defect here, you see detection of this. Distortion actually is not easy, and this is related in this length scale. If you like, this is a large length scale, component length scale. It's related to solid mechanics. It's related to mechanical engineer like yourself to help simulate it in the part scale. But actually, with using homogenization with not, but that not actually contains some microstructure information may not be correctly captured what happened during the 3D printing. Because the case in 3D printing is not homogeneous across the structure. You need to introduce some way somehow, a computational approach like statistical finite element calculation rather than more deterministic. You need to introduce some framework that they call statistical FEM. Another one they're looking at as well is another more rapid type from numerical way from computational mechanics. Is actually meshless, so you don't need to use mesh and then try to predict this part. Again, it's not my area, but you're welcome to study more in this topic, which is interesting as well. So you will see the residual stress in the principal direction as sigma or S33 at different direction or condition here. So that means you will see the different location, you get different residual stress profile, which make things even more complicated. But this is life, so basically complicated. And then next is a predicted or detection. The detection of the surface roughness. I mean, if your printed sample is in micro LPBF, and then this is for implant, for example, or thin film, you may use AFM, which is atomic force microscope to detect or measure it. Or if it's large scale, it may be some kind of laser kind of measure. But anyway, this is also, I think previously my colleague that I collaborate, he also used some microscope to roughly estimate. They measure RA quite good actually, but I have to go back to see the information how they did it. But anyway, this is some detection of the surface roughness, and the model also can try to predict what happened. In this case, some of you asked me before about how can we predict the size surface here, and there's some model actually has been done in a multi-layer fashion, but you will see here is about only 5 layers, but they can capture already the trend, at least quantitatively. But I think it's quite good agreement with experimental measured roughness here with very light energy density. But anyway, that means things need to be improved a little bit more. Another example is actually related to this evolution, but this is not, I mean, not really intended to be melting, but this is just sintered the part. So you see, if you scan these 3 track here and try to predict the evolution of the microstructure in terms of porosity, what you see is this one. Yes, you can actually, produce or create the process map PV, the same as you saw before. This is processing map, and you can see that at different conditions, this model actually flow 3D, this simulation. You will see that you can basically construct this PV diagram, and then this is what industry and scientists, engineer want to see how things actually vary as a function of this, and find a sweet spot or working condition for that. And definitely this is some predictive capability that we need for our community to advance further the 3D printing. Next one is about internal crack, and again this is related more on the solidification feature that you will see. The cracking actually depend on, you see this calculated crack susceptibility. This is calculation. It depends on the solute content. That means it depends on the elemental profile within your metallic sample, because we are talking about metal things, right? Solute content here at the different condition will vary as well, and these lead to different structure and also defect. Again, this you can do in terms of simulation that yesterday Hong Hao showed very well about how can you predict the the dendritic growth and the segregation profile. I can say it's not easy task to do, but that will give you insight that you may not easily experimentally measured. Next is related to what we talked as well in the past few days, is about the microstructure. So people try to predict or model this grain structure a lot. I mean, this is a work from Professor Wen Taoyan at NUS here, published in NPJ Computational Material. So you see multi-layer deposition and then capture the columnar growth here. But at the same time, if I'm not mistaken, this is from another group in Germany. You will see the kind of more kind of directional growth here. Even this is not single crystal yet, but this may be from electron beam melting that you will see the experiment and the simulation is quite good, in good agreement. Or very traditional kind of microstructure that you will see at the beginning of the research in AM of metal. You will see there, you will see kind of the band of equax columnar here. I think this is due to the melt pool that they not very much understand at that time to lead to this kind of phenomenon. I mean, zigzag pattern, if you like. Some structure is very zigzag, and that's why you see quite beautiful microstructure. I'm not sure it's usable or not, but it's this beautiful structure that can created by AM. All in all, what I want to say from this kind of work is about statistics that you extract and then try to predict. I think this is an important message I want to get across, that it's about whether or not you can generate enough statistics that capture the characteristic of the process or not. In this case, they try to extract the grain size profile, I mean, grain size distribution, I mean, aspect, I mean, this grain shape, sorry, this is the shape of the grain. One mean near equax, that mean, sorry, near equax, sorry, yes, that's correct. If you go to 0, it's more columnar. So this one is a left distribution here. This is more columnar grain, which is actually the same as you observe experimentally here. So simulation and modeling, simulation and experiment, I mean, probably tell similar things. It's quite good agreement that they can predict the distribution or stat of the microstructure here. And next one is about how can we model the microsegregation, which I think we show you a lot yesterday already on the dendritic growth, and then you see segregation profile here. And this is not artifact. This is actually real. This is induced by the process that you realize, and then we will have example very insight in the metallurgy of nickel-based superalloy in the next lecture. And this is how they use the discrete dislocation dynamics to simulate the dislocation structure. And this will be trying to predict the stress-strain behavior as well. I mean, under fatigue, I mean, that I said that this group, some group in US has looking at this very thoroughly, I think, in this dislocation cell for additive manufacturing. Yeah. This is just to summarize the first class about classification of defect that we are looking at. From you will see from thermal model. I mean, this one you'll see there's some calibration. That means that this may be a framework to reduce because the defect. So we start from the melt pool geometry, printability map that we showed previously, and then link to the experiment, statistical calibration. So this is the component that we're not talking very much, actually, but this is important because this information will go into use for the train of the model or whatsoever. So we want to extract some statistics and train it back, and then we hope that we can revise this process map, finalize the process map, and then print something, and then hope to improve the performance of the material. So in this cycle here, we basically need not only computational framework, but also experimental effort as well to make this kind of closed loop controls happen. So I think that is pretty much the aim or the goal for every company, university, research group and and everyone, I believe. So first, the cases I want to show you that why I put the data-driven first, because this will use some kind of data-driven framework to classify the defects in additive manufacture material as well. So this is quite a few years ago, published in Nature Com, is extraction of the defect classification in metal additive manufacturing. So you will see here they use titanium 6-4 to classify here. So they use a XCT, which is kind of automated XCT. I think this, if I remember correctly, there are about 3,000 or 4,000 samples that they classify. So the thing is, this is going to be statistic that you will get from this feature. So there are three important features to notice. The first one is lack of fusion. It will be lighted, elongated. And this is from XCT. I mean, this is the, gas entrap, the gas porosity entrapment. Yeah, gas entrap porosity. So will be smaller pore. And this may be during the atomization, is small pore in the powder. And next one is about keyhole or process-induced porosity, bigger size. Again, this is, we're talking about in the size of 10 micron to about 20, 30 micron, actually, size. And then they try to classify and map, because from the aspect ratio, you can basically classify what type of porosity. So basically, on the color code here, if it's rounded small, will be green. A big size, red, which is, green means probably, if you read it carefully, this paper, that means probably it's okay, not too harmful, but red is very harmful, it's too big. And the elongated is somewhere in between, but that means this, and there's some overlapping in the morphology parameter as well, because sometimes you cannot cluster this very, very well. But what they did is this. So if you actually looking at different sample, this is a distribution you may get from the classification. And then you see the dominant porosity is actually lack of fusion in the blue and the light blue here. Is a lot of lack of fusion porosity. Keyhole is quite minimum at the sample that they investigate on this 9 sample. And then there is a kind of intermediate, which is actually gas entrap porosity here. So this paper is quite interesting and show the good way to do data-driven with the data from XCT, which is experiment. So it's heavily coupled between experiment and coding. And then what they do later, they rank the morphology parameter to understand the extent of this on the overlap between sphericity, which is about the shape factor there, sparseness here, extent solidity, aspect ratio, elongation, this is a geometry, factor that they are looking at. So basically talking about the porosity only. What is the overlap between this gas trap porosity to the keyhole, gas trap property to lack of the fusion, lack of fusion to the keyhole. So there will be some overlapping, but this is something they try to rank in a pairwise manner to understand what is the overlapping percentage between each pair of porosity. And I think this is good and quite clever statistical approach that they use to basically try to extract statistics for this titanium 6-4 process. So later it's quite impressive again. So they implement this decision tree for defect classification, and then you will see they achieve about 98.8% accuracy of the test data. So that means based on, if I remember correctly, but it's thousands of data points. I think, if I'm not wrong, it's about 3,000 data or CT that they scan. But if you go to see the Nature Com paper, they will have an automated XCT system that they can scan this titanium 6-4 sample. Let's imagine how many data generated from that kind of measurement. But anyway, this quite impressive. So that's what I said. This is a statistic that they extract for different types, type A, type B, and type C. And again, later they put this ranking of the geometry defect here, feature here, into the machine learning or neural network here for defect classification. And that is actually show very well how experiment also doing some data driven as well. But that is the thing. Just want to say, so they have the two layer of deep learning, artificial neural network here. So this is the example that just want to show how they classify the defect and how important of this is. Because if you see here, if we don't get to understand this characteristic or suggest about, or if we can try to minimize this lack of fusion by about very minimum, distribution here, this is probably the goal that we want to control. But I don't think we can actually remove every porosity from your part, but it's about understand. You may not prefer this porosity profile for sure, but this one with a very minimum kind of distribution, the maximum frequency here, minimum frequency here, may be acceptable for application that we need. So I think this is quite clever way to have this systematic classification by artificial neural network. So next one is related more to what I have done. So the scale previously is in the porosity scale. Now I will bring up the scale a little bit to the crack scale, which is a little bit larger than the previous one. So I just want to summarize. This is from our recent paper last year in additive manufacturing. Just summarize. You will see this thermal signature curve several times now, but I hope you're familiar with that. So you'll see that we try to summarize the defects which is formed during additive at the different thermal stages here. From the argon atomization, you may get entrapped, gas entrapped porosity as well. Free alloy may introduce some compositional defect here. And then when you go to the particle solution with intrinsic treatment, you may get the different integrants, cellular structure, and then also dendritic and solute trapping cellular structure here. Again, you may not get the quite homogeneous profile as printed, but some of our work shows print soft. That means it's solid solution in the print, and then you may be probably you may get single phase, but sometimes you get anisotropic of the phases. When I say anisotropic, it's not in terms of orientation only, but in terms of the phases present during printing. So you get gamma. In nickel-based superalloy, it will be gamma prime, but you may get only gamma, but small amount of gamma prime. We show you, I think, probably more tomorrow as well. And then there's some anisotropic, which is actually happening in the preferential gamma prime, and anisotropic of the randomized gamma prime can happen in the post treatment. And actually, you want to get to the end to the isotropic gamma prime distribution because of the you want more homogenized structure for the property and material life at the end. So this is just summarized, but we are talking about the possible solid state defect, which is bigger length scale, but it's not too big. In this complex nickel-based superalloy things, you will see that we get a kind of stranded crack here. I'm not sure you can see this one, but related to very tiny gamma prime particle that decorated around that crack. So we also have the stationary cracking that transmitted across the melt pool, and probably it stopped at the solute trapping zone. I think this is another topic that I want to emphasize from next lecture and tomorrow. And then you'll see this is how science and metallurgy can probably give insight into the kind of defect formation. And then you may get some kind of liquation of the, during the 3D printing, there's a liquid film which is formed during subsequent solidification, and this is quite not new things. It's happened as well in casting, but in 3D printing, it's commonly found a lot. So, but no one really know this one. If it's not very metallurgist, they may not realize this is this liquation cracking, something like that. It's related to the incomplete solidification and then left behind some liquid film inside, and that is a weak part for the cracking. And actually, another one is solidification cracking. It's near completion of the solidification, but it's actually tailing off, probably due to other factors like another mechanical profile surrounding that, or due to the geometry, residual stress induced or whatsoever. But if we kind of conceptually draw the strength and ductility profile here, the strength will be good when you have quite homogeneous structure, but it will drop significantly, or this defect will make it drop significantly, and it's the same as ductility. Good when you have homogeneous structure drop and rapidly recover back at the matrix. It's a pure nickel FCC here, and then drop again when the defect kicks in. So I think this is good. Tony Tang, which is my previous postdoc now at assistant professor at University of Birmingham, has done this very well. And then what we did next is try to systematically investigate the crack which is present during the 3D printing in 4 nickel-based superalloy. So if you remember, we introduced 2 new nickel-based superalloy ABD series, ABD 900 and ABD 850, and then compare with Inconel 939 and CM247. We printed in a 10 by 10 millimeter cube here using this scanning pattern, and then we rotate by the factor of pi, so 67 degree for the scanning pattern. And then we evaluate the crack for each material, each nickel-based superalloy material. And what we did and we found is that the porosity actually taking place at different location and occasion. What does mean by that? If people actually have some bias on the characterization of the 3D printed sample, they usually take and select only the good area without crack and publish it. But we think this is not actually good for machine learning later as well, because the data that we will correct from literature will be biased. But what we did is actually we map using mosaic kind of approach from OM, optical micrograph, SEM, to map across this 10 by 10 millimeter. It's a huge area. Not usually people will do this, but that is what we found, the crack at the edge related to the different, I would say, heat transfer coefficients between the edge and in the bulk, and that means you get different structure. But anyway, at the edge, in the bulk, we call micro and macro cracking here. And this is what we'll see. That is why we always show at the edge. And you'll see this is 2 millimeter. It's quite large area. Actually, we show you here. This is basically the whole sample. So you will see, you can get an overview, the map of the crack. And what we do next is actually we compare with the newly designed alloy here. There's no crack or very minimum crack. We will show you some statistics later. So this, you will get some lack of fusion porosity in this type of thing. That means it's related more on the process parameter optimization rather than other issue. Yeah. But in other cases, like CM247 is quite severe. You see it's a kind of, I think, super macro crack that actually can crack your sample. Even this is quite strong metal. But if you do some quantification of the cracking, you can plot the distribution again. So, Joseph, our previous PhD or DPhil student doing very well, that you can see the crack length from the image you take, and you will see that 939 actually quite a lot of crack length compared with, in terms of distribution. And we summarize that the different alloys are found to print optimally at different conditions. I mean, everyone knows, but how can we have statistical evidence like this to prove that how different? This is the question. It's not about only printed different and crack. So we quantify this for the whole 2D. At least it's not 3D yet, but it's a whole 2D section. It's several sections along the build direction that you can get some statistic. Again, this is not easy job that you need to do a lot of experiment to do serial section of this one. And this is basically related to alloy dependent, the crack, that we use a non-equilibrium Charles model to try to predict. Because as I mentioned briefly previously, if you have the kind of facing range larger, you tend to have, you're prone to have some more cracking than shorter facing range. And this is actually confirmed by the model that the facing range in CM247 is almost 400 degrees centigrade. There has a very large gap of the temperature that crack can form. Compared with some new alloy design, which is about reduced by, I think, more than about 35% less facing range than the very non-weldable or very problematic alloy here. So this one shows that this thermophysical property contribute to the cracking that you see here as well. And I think this is very beautiful image that has been cited a lot now since it's published, and also referenced a lot in the textbook as well. That image here has been selected carefully from location to location to get to the point where we see this solidification cracking to confirm this is really solidification. You see the dendritic arm here. And then it's not just that, because previous work from the quantification, you show there will be some overlap or correlation of the defect. Again, there's not yet has a high throughput way from the experimental way that we can characterize or map this. Because nickel is probably more difficult than titanium. You know, the density of nickel is about twice of the titanium. And this may pose some challenge in terms of XCT when you may have smaller sample size than titanium, for example. Yeah. So we tried something already as well, but next one is actually the second generation, which is 900 AM, and first generation new alloy, which is 850. You will see it's almost crack-free sample. We not actually selected some area, but every area in general is like this. When we map in the whole sample of the crack map, you see it's proud to be printable and crack-free. It's not just printable and crack-free, but if we confirm with solidification range here, when we compare with the chart, which is non-equilibrium and equilibrium calculation, I mean, we use thermal calculation to compare and calibrate and verify. You will see that the new superalloy actually has a very minimum fishing range, and then compare with CM247 and the 939 here. And that's why this finding rationalized through the traditional hot cracking approach. But what is actually happened when you are here? They expect to have about 25 to 35% gamma prime, but it's print solid solution. It's print solid solution. I can show you in the next lecture. It's proved by so many means of experiment. It's solid solution. But that's what I said to you. We print soft, and then we recover back the strength later. This is what it does. So previously, if you use just weaker hardness, it's actually quite soft during printing, especially here. But you can recover back by one single heat treatment cycle, that you can recover the strength back, precipitate out the secondary phase. So this is probably something that we cannot just simply dream or speculation. It's happening here in this very systematic investigation here, that the property along build and then transfer direction actually quite similar. It's not very mismatched like other. You see, if it's very anisotropy, it will be quite different. Microstructure, let's say, microstructure of the metal. I mean, this is another insight, which actually also this, if I'm not mistaken, I'm not sure is at a nature com or advanced material. You will see that this is just one melt pool, but they map very high resolution. And what you will see, this will lead to the next topic that I'm going to talk is about macro segregation. But you will see that the melt pool boundary here decorated by the equax grain, whereas the transition of the columnar is going this way. So this equax columnar transition is happen in this layer. But actually, if you look at this clearly and closely that we did, we found that this is some interesting different solute or segregation profile in the melt pool boundary that we call solute trapping during rapid solidification that we will talk more in the next lecture. So you will see that the microstructure across this one will be different if you draw a line across. I mean, this is a scanning path related to the microstructure you see. So people now in industry try to relate this as well in the final part of the product. How can they link the process? I mean, this is show how to link the process with the structure and property. Clearly, yes. So this is the way we scan this direction, sorry. And that is the traditional, again, just to emphasize and re-emphasize again, this due to the thermal diffusivity of the metal and lead to the different melt pool geometry that lead to the different structure here. As I told you before, increasing the well speed, you get kind of doublet shape. I mean, the water drop shape here. And then this lead to different columnar grains microstructure. This is standard solidification theory, looking at the growth rate of the grains versus the thermal gradient here, where what is the zone of your microstructure will fall into. But it seems that the growth rate and thermal gradient is very high. It should be in the zone of stellar and planar, not really columnar and equax that we want. But this one will fall into this after some time. It's not immediate. If you scan one track, you may see mostly stellar or planar structure. So this is the work that, this is not 3D map, but anyway, that's represented in 3D, but looking at a different section that you have in this way, and this way. And then you see the microstructure at 3 different locations are different. Evidenced by the statistical approach here, a whole figure, which you know is a collection of grain ID here that you map onto this stereographic orientation. And then this related as well to the process. You see with different, melt pool shape. Here that this paper try to relate very well that most cubic material preferred orientation is 001. And this is a strong texture direction. But this texture we call tailoring. We call the texture control in additive as well. Yeah, we need to control this texture to align with what we want, because the property will follow that. Again, this is actually not 3D printing, as one of you has pointed out, but just want to show that okay, we have chemical segregation, we have different cellular structure, we have actually grain boundary, and also this location cell here that map quite well that the microstructure in AM is very hierarchical. This is what the point I want to make. I mean, this is steel. I'm not sure, I can't remember which steel, but this steel material. And then this is the things that we want to emphasize. The microstructure from the length scale point of view is actually from nanometer to about nearly millimeter length scale. We call this, there's some hierarchy in the structure that you may extract from from experiment. And now modeling try to predict that at different modeling computational framework that used to approach or used to try to understand, predict that. Just want to show here how hierarchical in our, you see we have one 10 by 10 by 10. So just follow my slide. Clearly the next one, we map across this 10 by 10 by 10. And then we zoom into the corner of the 10 by 10 by 10. So this is just half millimeter. And then we map the EBSD at this particular section in that corner. You will see this is surface connected, and then this is columnar grains, as I mentioned before, the bulk. And then when you zoom in a little bit in the columnar grain zone, which is mostly the zone where you found a lot of crack at the edge, right? And this is something you can see. But if you zoom in another more, using the high resolution EBSD, you get the map of this zone, and then you will see that in a single grain, there is a hard and a soft phases. So residual stress, a type 1, type 2, type 3 can be all extract from this kind of study. So there is a softer and stronger part in one grain. And if you try to say, residual stress across the crack here, this is a profile, and this quite heterogeneity. Oops. And then this may related to the microstructure. Now I'm going down to nanometer scale. It's may related to carbide. This is Incona CM247. And then this is at the edge as well. There will be heavily element segregation. Again, this all of the thing that I mentioned is all linked together to the cause of this problem. And then after that, we also identify around this a liquid film which is formed during the process. So I think I just want you to, appreciate this is something that we try to look at. And this liquid film, if we looking further into the sample, you will see some hafnium more, and then some carbide and tantalum in this crack region. So it's quite amazing work that we use all the characterization technique to provide insight into the defect formation during the process. And this is, finally, we want to control the structure. There is no doubt about it. But in order to do that, because people try to do, rapid calculation. This is an example from Professor Babu at, Knoxville, in Oakland. Can't remember the full names, but you will see this aluminum alloy try to predict the columnar equax transition here. And then just wait a second, you will see how melt pool actually in a large scale here. This is more like a reduced order model here, that they can predict how likelihood of the region where you will see larger melt pool or smaller melt pool. And then that's each dot represent the printing area. So you can map roughly from the thermal model the G over R, so you can extract the microstructure approximately. But that means your thermal model has to cover enough to capture the characteristic from this diagram. But again, it's not ideal, but it's a way we can rapidly calculate the area or region where we are interested in. That's why people talking microstructure control. Everything is only from thermal signature, actually. So this is how they control it. If you control it well in the electron beam LPBF, someone asked me yesterday about what is the scale. This is quite old now, 2014 or 16. They proved that if you control thermal gradient very well, you can get single crystal in electron beam melting. So the way they didn't say much in detail, but according to private conversation, it's actually just trying to make the thermal gradient simulate the thermal gradient that similar to casting condition. Because in solidification of casting single crystal, you will need to control the thermal gradient very well, right? This is the way, it's not the principle is something we can know, but in practice, this is something difficult. How can you get that condition? And this is only happen in vacuum condition, which is the same for single crystal casting as well. They do it in vacuum. So that's why electron beam melting is possible to make this happen. But the scale, maximum scale they get is 5 millimeter. I don't know now, probably latest development, they can get bigger component to do single crystal. But this is 5 millimeter thick, and then this is one crystal grow. Impressive, yeah, by Kroner, Professor Kroner at Erlangen in Germany, yeah. And this is DOD, I mean, in USA, for sure. This is just for how fancy they can control microstructure until you can see different grains at specific location that DOE. That's what is told by this kind of beautiful color diagram. But that's quite impressive because they showed this long time ago, so they know how to control this. But how can you make it in practice? That is probably another question as well. So people know and can control it. Residual stress also a way that we found is problem. I think I showed briefly previously. We went to Oak Ridge National Lab as well during my time at University of Birmingham. And then this is CM247, I think. And you will see the residual stress profile across these actually 30 or 40 voxel point measurement here. You will see the profile is not homogeneous anymore. It's quite asymmetry and heterogeneous in general. This is partly due to the defect content in the sample, as well as the, a printing condition is contribute to that as well. So if you map across different locations here, you will see the maximum, stress, residual stress, predicted residual stress at different locations are also different. So there's some combined between compressive and compressive stress and tension and tensile stress in this one sample. So we need to be careful, especially scanning pattern will contribute to that as well. So I mentioned 4 parameters now that we may need to be careful about this, because the microstructure information of the sample will be so significant that we talked about defect content previously that contribute to this residual stress. I think this is a proof that I'm trying to say from experiment point of view. But if you want to actually predict the residual stress, it's also possible. This is by Professor De Broglie at Penn State. That time they tried to use computational approach to predict in canal 718, if I'm not mistaken, along build direction. You will see profile is quite similar to the segregation profile yesterday, that you get different zone of, you get a blue spot here, which is a bit compressive, and then it's tensile at the edge. This is quite classic. It's also happened the same in welding as well. But this one is rather severe and unpredictable because the shape here is also, the sample is also distorted as well. So asymmetric residual stress profile has been observed and measured. How can we predict it? This is another thing, and then we need to deposit. I will show more a little bit about residual stress prediction as a function of microstructure later. This needs to be discussed and require more understanding in another alloy system. It's not just nickel-based superalloy. So this one, what we try to do, we try to model what happened in the previous slide as well, that we're looking at different microstructural content, assuming that this component has porosity preferred in one location. And this actually contribute to the asymmetry of the residual stress profile calculated in the MATLAB, in Abacus simulation here. And this is actually confirmed why further research is needed when you're looking at different components, different material, different process conditions, to map all this information into your calculation or designs, engineering design framework whatsoever. Another one is also a defect in the static loading. So we're talking about property microstructure. I don't think I cannot miss property in terms of static, in terms of the tensile stress. But the side effect actually has a lot in the titanium 6-4. This is for, they try to develop this company now called Alloy, try to develop a new titanium composition for biomedical application. And they found that in the titanium 6-4 medical grade, when you print a different size, from a quarter millimeter, half millimeter, 1 millimeter, 1.5, 3 millimeter, you get the side effect in the different orientation here. And this is quite impressive that you can actually get different ductility. Even the stiffness is quite similar, but ductility will be varied based upon the size of your sample. And this is they compare as well with non-AM material. I mean, the yield stress in AM proved to be higher than the standard non-AM sample in Ti 6-4 material here. This is quite a good systematic study that you can follow. I think the paper is published in Acta Biomaterial and Material and Design, I think, back in 2014 or 2016, something like that. Yeah, 2 of them. And then this is due to as well from the solidification point of view. So it's not just printing as printing. You need to rationalize why it happened like that. Why the surface roughness and solidification structure may contribute to the property that you see. So the argument is that for the smaller sample, the dendritic arm actually coming from the side, and then it's trapped something in the middle. Trap the columnar grain in the middle, whereas the bigger sample, you get more columnar grains, which actually more detrimental for property. And then that's what they found. And you can follow this work as well on paper. Last but not least for my section not finished yet, but this is just static of fatigue creep. You will see that at different, whether or not you have AM or machine from AM or rod AM to fit this, you will see the different material manufacturing process contribute to different cyclic or we call time dependent property here. This is the fatigue, the number of cycles to failure here. You will see that for the non-AM one, this is one thing, but if you have AM, but you machine the sample from the AM build, they get the different property from the as printed sample as well. You follow me? If you print it and then pull it, it's different from you print it, cut it, and pull it because of surface effect. So this is what happened. They study this. Why they need to study this? For example, if this one is actually titanium 6-4, and then you want to print for implant, I don't think you can do any treatment for the surface. So you may use this implant from scaffold or whatsoever that you want to use. So that's why you need to keep the surface as it is, right? This may be good for cell growth, but if it's actually AM, but you cut it for, remove the surface, this will contribute to the different in-phase, fatigue life here as well. And this is quite clear. It's really happen. If you machine it, it improve a little bit the property, but not very close to the rod material. But if you as printed, I don't say the worst, but you still get about probably million cycle of life of material, but it's not as good as 100 million cycle of the material life. But anyway, this is something to consider. I throw this question to the mechanical engineer to try to solve and understand. That's why the detailed microstructure is so important to dictate the life of the material in this case. So no doubt about it. And people trying to quantify it as well as a function of, you see this is inclination 1/8. If you cast and rod alloy, you get the maximum property here, creep property here. And if you directional, I think if I remember correctly, kind of traditional process, I can't remember DA, what is this? Yes, is, yeah, you get property which is decreased by half already, half the creep life. But as built and STA, this is the property. So how can we shift the property from this to the right? This is the key. And this is it's actually pretty much on the crack content in your sample. And they use the this is not atom probe, this X-ray tomography to quantify that. And then we also do the same as well for our sample. But this is a cracked and uncracked sample that contribute to the creep property. Again, from fatigue creep is so important. And this is so difficult, not only just model, but also expensive to measure as well. It's so expensive experiment. So I think it's a long time, but just want to get back to nickel-based superalloy and probably just want to quickly summarize why I do what I do. I want to say that when we have defect here, we predict porosity. This is old slide, just to introduce something, and then you have different predicted secondary phase formation, and also during post-treatment in hipping, you can get different distribution of the size of the particle, which is important for the material life prediction later. So this is the thing. What we do, we actually try to classify as well from simulation. I think this is my work. Lack of fusion or manifold porosity, and try to map across the composition as a function of process parameter. In this case, it's surface. That is a layer thickness. But what we did, this is something I want to suggest the community. We predict the distribution of that. So this is similar to what you've seen from the previous slide, that the way forward is statistical finite element calculation, that we predict the shape and the radius from the CFD simulation. We extract the distribution from the simulation model. The more, the better distribution that you will get. So this is the way forward, that you plug in this into probably some of this one. If you remember this slide yesterday, so this one coming from the lower length scale calculation. So you see now how we link CFD to path scale analysis. That's my point to make. So this is the information that we transfer across the scale. It's maybe this one can measure from experiment, that's fine. But you see how expensive you do that classification for titanium 6 soil is. It's almost impossible for every group to do it, right? It's just very rich, super rich group that can effort doing 500 sample of Thai 6 soil in XCT. Yeah. This is, anyway, this is probably we can move some of this to the next session. But I think it's quite interesting thing that also interested me as well. So I can talk a lot for the, now we move up the scale a little bit from, previously it's on the micro scale. Before that is in the Melpool scale. And then we move up to path scale, a little bit path scale, but not very path scale, but try to predict the residual stress based upon Melpool prediction. So this is what the framework they want to predict. This is from Professor Yan at US. So you see them, this multi-scale, multi-physics simulation for the Melpool to get the grain growth. And then you try to get this kind of profile. Quite interesting that you can map plastic strain across the Melpool quite accurately, because they validate with lattice strain measure in a synchrotron experiment as well. Modeling and simulation that they validate across the length scale. And residual stress in the sample you see is so heterogeneous. It's everywhere. And I want you to notice that this map of residual stress is not the same of the welding residual stress profile that you get compressive and tension. That's because it's actually everywhere. you see this profile. And it's because of the different residual stress in type 1, type 2, type 3. In the grain, inside the grain of blah, blah, blah. I think not want to mention much about that. And this can be predicted, but it's not easy. But this is what they do. They do two cases like me. If you remember my lecture in the day 2, we're talking about full penetration and conduction mode. They do the same. But the way they do is actually they extract thermal gradient, which is important for the microstructure model later. And then the heating rate. Why heating rate? That is a good question, but actually heating rate will tell you about during cooling, right? And then cooling is something we will use from this model as well, but this is show the heating rate. And next, they set up the two cases in the full penetration. Again, you will see the model domain is small, like what I did. Well, otherwise, it's impossible to do it. And then you have case number 2, which is more equax. On this is actually conduction mode. This is 2 cases here. And then they can calibrate the residual stress profile at different 3 principal directions in x, y, and z, sigma. Yeah. You will see this, the keep is normalized in z direction the same way as experiment do in the neutron diffraction experiment. So they set 0 at the along view direction, and then to see the profile in plane stress strain condition. Because they want to validate this with the critical shear stress, resolved shear stress here, first simulated an experiment. How close or calibrate, if you like, calibrate the model, what is the critical resolved shear stress here. So you will see the modeling and experiment match quite perfectly, not just well, it's very perfect. So we can get some critical, again, I would say there is some comment here. This may be the not 3D printed sample, but in this case, maybe 3D printed sample, but some cases probably not, right? You may not have the data for that, for material investigated. Yeah, so and next step, they try to do the export this one to predict plastic deformation and residual stress evolution. On the left hand side here, this is the laser in the center, and then I think this is the same but different time step. Different time step after cooling is you actually pile up the residual stress and plastic strain here in both full penetration and the how to say this is keyhole mode and the conduction mode here. You see some residual stress profile here, and then you can map as well the same way you did in experiment that I showed you previously. If you remember my slide at the EBSD, high resolution EBSD, you see the soft and the hard grain, which actually seen here as well. Some grain is not actually single, for example, this grain. So you have some, different stress level. Type 2, type 3 is actually kick in. You can draw profile inside the grain, and then this is quite impressive. If you do some high fidelity model, they can review this, and then they try to say about the relationship of this, and then they try to extract from from simulation that what happened in the residual stress profile after cooling and relaxation. Residual stress component is in XX and ZZ. Yes, and then you can see how is the question he asked is quite interesting. How is heterogeneity of this residual stress induced by the grain orientation or not? That means if it's linked to grain orientation, you can impose some way to tailor the grain, texture, if you like, it's the same thing, right? How can we get texture correctly at the beginning? That's why we can control residual stress. And this is how they map from experiment. You see a band of a soft, I would say compressive and tensile grain, I would like, at different location. And the correlation of this may give further insight into the simulation and experiment to change the practice doing printing or find some way to control grain orientation texture, for example. So I think I just want to finish here for this one, and then probably continue the second part, some part of this in the next one, and then I will show some I mean, very inside example about how we design nickel-based superalloy as well. So summarize for this section, I mean, this crystal plasticity model here. In the micro scale, crystal plasticity model has been implemented in the micro scale residual stress in additive manufacturing. And temporal profile actually used from thermofluid simulation. Okay, it's coupled now. So you see how things transfer across. Grain growth, predict on phase field grain growth, which also coupled with the thermal fluid. And then this simulation validate again in situ X-ray diffraction on AM sample. And this relation between grain orientation and residual plastic deformation is revealed, which is not seen something like this before, right? With experiment, it's probably hard, but this one you get the basically time resolved residual stress profile from modeling. So this is why high fidelity modeling will be very beneficial, but it's in the same time it's hard to do. But having said that, I think you agree with me that the picture that I'm trying to show to you, up until now, nearly the end of the course, you will see that this is so relevant, and then it needs to be combined between physics-based and data-driven. One alone is not possible, so we need to work together. With only data-driven is not enough to get all these features, if you agree with me. And with only physics-based model, sometimes you can survive in academic, it's okay, because you're interested in more very scientific curiosity, working with some fancy scientists around the world. But the question, is that useful for the real use? That is another question. So the better solution is to work together and then to get the better technology for the future. Thank you very much. Any quick small question? We have about 5 minutes actually. Yes, please. Yes. Yes. I think I mentioned this point already. That's mean the range, because as I show you in modeling, there's some is stochastic. So what you want to control is statistic. You cannot expect to get one point of measurement now. You need to know what is the range of, or what is the distribution of your porosity or microstructure, and how can we minimize that distribution. I think that is the key. But in order to do this, we need data-driven, right? We cannot just, run or do 10,000 of experiment to extract that. Combine between model and target characterization, I think. So I think this is the way, and hence you will get the distribution of porosity, distribution of microstructure, and then distribution of property. How can we reduce the noise? So that means some other mathematical framework like statistical mechanics, for example, may kicking in, and I think this is probably the future. It's happening now. It's not future. I think you know. Yeah.
Sir, and one more quick question. So, in one of the slides, you have mentioned that you came up with a novel material which is completely porous free. So, what about the scalability of that material? Like, can we able to print such a larger sample even without forming any porous or cracks?
I think you asking the good question, because next slide, I will show you the new material that we design. We use in rocket engine already. It has been used in US, yeah, ABD 950 series, yeah.
Sir, we agreed that modeling can be used to predict stresses or strength for any kind of printed materials. But in the case of defects, can we able to predict such defects through the modeling?
That's what we do. That's what we try to do. We try to improve every day.
So basically the defects can be depending on many factors. Is it possible to give all kinds of factors in the modeling?
This is number of paper. I would say number of paper now study different individual aspect of the defect. So once we combine this understanding and then build a framework, has to be data driven. I think with the informed by those kind of lower length scale understanding, I think it's possible to get a framework. But I would say it has to be collaborative effort. It's not easy job. As you know, everything is actually overlapping couple together. So the best way is to have a kind of showcase. When I say showcase, just focus on single material like they do in Thai 6.4 and try to make it multi-scale characterization and modeling and see if we can showcase this is the thing that when we link everything together, we will get better solution. I think that is why we call digital transformation is important.
How much percentage of accuracy is possible, sir, in predicting the defects?
At the condition investigated, it depends. I'm not sure. If you talk about in a very controlled manner, which maybe you're talking about Pascal, right? I don't think if there is something exists on Pascal, it's not published yet, as far as I know, because it maybe belong to some company. But as far as I understand from our low length scale prediction, it's accurate enough to capture under condition investigated. But in order to translate this accuracy to the large scale accuracy, that is another question, because you need, that's what my answer is. So you need to optimize properly for this part, not only in the very controlled volume and small sample. So the question is not about whether how accurate we can do accurate prediction for this given length scale, but how can we translate this accuracy to larger length scale? That is another question, which is actually, that's what I'm trying to push forward the community to work together for that. Yeah.
The last question, sir. In the particular slide you shown experimental and analytical graph. So you showed 100% accuracy. So it seems to be overfitting. Which one can be accepted?
We call calibration. We need to fit something to the model first, and then at that given condition, or we call verification of the model. And we know, we fine-tune the model until we know that is the condition for critical shear stress, and we use that to generate all other data. And that is normal for any computational framework, even characterization technique. You need to calibrate with something, and then you make sure that this is correct at the initial condition, and then you do. And do you agree with me? Yeah, otherwise, if you want to ask me like this, no neutron diffraction is correct, because you actually assume something only in, I mean, I can discuss on this in a lengthy discussion, but anyway, we need to calibrate something, and we need to believe this is correct, and then you use this to predict something. Yeah, I think that is the point. Yeah. Thank you. We need to fit something somehow anyway. This is science. We need to assume.
Actually, I want to ask, you were sharing one slide related to the calibration of the models, right? So while calibrating the model itself, what are the parameters that should we look upon from the model perspective when we calibrate or validate it with the experiment and calibrate our model? So what are the parameters that we should look upon?
Yeah, so because we need to find a parameter that we can observe both experiment and modeling. So it won't be some parameter that you cannot think of. It may be simple as probably just stiffness, just a young modulus, shear modulus, or something like that. It's not something fancy that we need to calibrate. But in order to get those parameters, you may need to work out in the crystalloplasticity framework. You need to work out the coefficients. Let's say, I mean, for example, I make it up now. For example, you just need, because it's happened because of the slip activity in different plane in your crystal, right? That one will coming out after you calibrate this one. So those parameters will be used for further calculation. So that's why we need to we have the global and local parameter we need to calibrate. So we need to calibrate something. What you see is actually global result that we show you, but in local, we also have another set of parameters that we use for further calculation.
So while doing such calculation, there is no need that the global value of the Young's modular should be equal to the local value of the Young's modular. It shouldn't be like that, no? Means it can be different if we calibrate, so it can be different from the global value. It can be different.
Can be different from global value.
So suppose if we are calibrating it, then the Young's modulus is of steel is something 200 gigapascal. So if within the crystal plasticity model,
Yeah.
if we while calibrating with the experiment, if it deviates from that value, is it okay? Means
Yeah, but that's not too deviated, not like 200 and 1,000 something like that. But I mean, I understand your point. Yeah, that's what we do as well. Under the accepted percentage, something like it's also possible as well. But I mean, I'm not very expert. I can't remember as well. But the mechanical engineer may set around, I think, 1-digit percentage, right, that you accept to as a working model, for example. So I think, yeah, that's what the practice in the community anyway. I'm not saying something new. Yes, please. Yeah. Oh, that's his next lecture. If you spare this question for next lecture, it would be good. Thank you very much. I think we have about 25 minutes, I think. Yeah. Thank you. Yes. So we will continue from the previous lecture. Just one last example before we go moving to the microsegregation and the dendritic structure. And this is electroplastic residual stress analysis in the sinter porous material. Again, this is use laser as a sinter. So probably this is a bit different from the LPBF. The difference is actually this one is diffusion-driven process. So you use laser to just sinter the material together. So you left behind porosity. The same processing technique you use for ceramic, but you don't need laser, right? Since ceramic using electric field to do sinter or spark plasma, you use a quick electric field to basically sinter it. So they will fuse particle together. But this, what they do is actually they do similar to LPBF, so they have powder bed as well. But it's cheaper in terms of laser heat source that you use. And then you use discrete element method here. Oh, sorry. Discrete element method here to spread the powder. And after that, you use the finite element method phase field simulation here to scan to sinter the powder. And then after that, you use thermoelastoplastic simulation to basically calculate the layer 4. Within different, this is one condition 4 layer. This is second condition. Oh, sorry. First row is actually one condition but 4 layer. And this is the different condition at the layer 4. So you will see that this is a thermal cycle for each deposition here. And then I think it's probably difficult to see, but you will see that the thermal cycle will be not that severe compared with LPBF, the real LPBF with melting, but it's basically capture the trend of LPBF somehow. And this is the temperature normalized by the melting temperature. So it actually dropped to about half of the melting temperature, not going to the room temperature yet. So this one, what it tells us is actually we can then later relate this thermal field with the residual stress build-up profile. So we'll see this will be oscillated residual stress profile, based on the Wall-Mises stress calculation here, and different layer. So you will see how residual stress building up, as a function of layer. So it's quite, uniform, but uniform not in the sense that, it's not actually go back jumping a lot, but it's actually oscillated around this 200 megapascal, whereas the plastic strain actually start building up like this. But there's some phenomenon which is interesting, because normally you will not get plastic strain in the slope need to go up all the time, right? Because one is permanent deformation, they won't be able to go back. But there is something interesting that we can discuss when they get it inside based on the processing technique here. But what I want to say is that this kind of thing is become more and more common now in 3D printing community, that we use the very multi-scale model to keep inside. And for this case, this is 4 layer. Probably it's already enough to capture characteristic of the process that may be necessary for next scale simulation or whatsoever they want to use. And then you will see that the residual stress profile is quite complex. And if you vary the location as well, I mean, this is different stress component, you will see that, I mean, even the shear component here, you can extract. And they are behaving differently from the principal or normal component. So quite interesting and give insight. And this is difficult as well from neutron diffraction or diffractometry perspective. If you want to rotate your sample to the shear component, it's quite hard because you need to have rotating table that allow you to move for some certain angle to do that. I mean, yeah, but anyway. So what you do, they can extract this kind of the Warmises sphere, I mean ellipsoid as well. For I mean that they extract for this. So this is very exciting work actually, because this will give a chance some light for other model that they can use. But I believe they use 4-3D to generate this data. So they cooperate with them. And then you will see unfilled particle or structure here will contribute to residual stress some way, somehow. And this is shown that plastic strain and residual stress is not homogeneous again, like before. And as a function of the porosity, which is trapped inside. So this is something quite exciting that probably we can better design the material to avoid this to happen if at all possible. So they again try to do the process map, which is quite complete set of work that they can produce PV diagram and then try to identify mechanism for each parameter zone. And this is the thing that as a community we move forward this and to optimize this PV diagram computationally and feedback to do the closed loop control for the 3D printing. I believe we all agree that this is the way forward, which we need to go ahead, and either experimentally expensive way or computationally a little bit less expensive. It's require different skill set, or probably similar now, but modeling may be more. And the reference here showing different, how to say, I can't remember exactly, but anyway, this is some comparison with the, I think, energy with the a plastic strain or something like that. And then you have different PV diagram at different, I think, a little bit different condition here as well. I mean, set up. And that actually contribute to the prediction of the plastic strain and then the residual stress profile compared with experimental work as well. And this is, it depends on processing condition. Yeah, I'm right. And this is depend on the processing condition that you will get different, I mean, profile. So quite interesting to look at and then understand what happened during the processing of this specific material. So having said that, I think this is something about defect that we want to mention to you that is really important to identify the defect, classify the defect, and then trying to how to say, control some way somehow using the numerical or experimental method to allow you to do that, to control that, and then you can print with defect free or print solve harden later, for example. Next one would be not too long. If it's not too long, it's not many slides, but it's about a kind of success case that we do using simulation. So this will be last two presentation for me. This will be the second last. There will be, first one is about more physics-based modeling, about multi-scale, multi-physics modeling. Another one is more combination of the data driven or machine learning based on alloy design combined with experiment to do about ABD series material, for example. And this is actually the work that we recently published in Nature Communication on the solute trapping that will show you some insight about what we have done and what is a way forward for the community on a systematic study on a system that we believe this will be important for the future as in terms of the compositional defect or micro segregation. So as mentioned, this will based on this paper published last year, early this year. So on the topic is on the solute trapping. I'm not sure anyone here understands solute trapping. Are there anyone in the metallurgy field? Good, good. So what do you think about rapid solidification? What is an important aspect, and then why is solute trapping? Can anyone tell me a little bit more? Yeah, can you tell me what your understanding about this solute trapping or non-equilibrium microstructure and rapid solidification? Yeah.
So if the solidification rate or temperature gradient are very high, in that case the cooling rate will be very high. The cooling rate, if it increases, what will happen? The amount of time that typically we have in casting process to allow the element to segregate out, we will in very faster cooling rate will not be able to segregate out, and they will be trapped inside, and there will be metastable phases forming in the
Right. If I get a more clear example, yes, please. Right. Oh, you mean phase transformation now is not melting, right? It's after, you mentioned it's after. Okay. And then, yeah. Okay. Right. Right. Okay. Yeah, but it's not. That means it's not necessary. Is that necessary to happen only in additive manufacturing? It can happen in other cases. Okay. Yeah, we call bulk metric glass. Yeah, but anyway, that's all correct. Yeah. Another question. If you know solid trapping, can you comment on the eutectic formation during the alloy solidification? Okay. Sure. Thank you very much. So thank you very much for your engagement. So what you said is completely right, but what we are going to say here is solute trapping in our case is due to the rapid repeat thermal cycle in additive manufacturing that lead to something, as many of you said, non-equilibrium, non-uniform microstructure. And this is still unclear. How we try to understand this is to try to use the multi-scale, multi-physics model to give insight into this phenomenon, what happened, especially this one for nickel-based superalloy. I think I didn't say much here, and understanding of equilibrium nature of this intercellular solute segregation. So that means we try to resolve how this dislocation or cellular structure profile happen as well. So it's a bit scientific, and I hope you enjoy it some way, somehow. So what we are going to talk is give you a little bit background and motivation why we're interested in this work. And probably you may hear enough about nickel-based superalloy, because this is my research area for a number of years, that I'm talking a lot about this, and titanium as well. So what is a typical microstructure of AM? And we'll focus more particular on the solute trapping using the number of characterization technique, not only speculation. We need to observe something and then inform the model what to do. And then what is a heterogeneity that I show you a lot in the past lecture already? And how can we actually predict or do something about this heterogeneity? How can we homogenize this or not? Or what is a characteristic of this? And then method that we're going to look at is actually, basically the first item is CFD, is melting based additive manufacturing. And then there is a solute trapping and elemental profile of the cellular structure. So the highlight here is cellular structure. How can we predict it? Actually, if it's happened in the melt-pool length scale. And what is the thermal mass solute transport during the deposition of the 4 nickel-based superalloy we'll show you later. And this, how this one induced the transport, this one induced to the structural evolution. Structural, in this case, in microstructure evolution during printing. I think, please bear with me if you're not in metallurgy field. So I'm trying to go as slow as possible because we believe this one actually influenced of the solute segregation here in superalloy, important factor for the crack susceptibility. So I will try to link this based on analysis that we done up here and try to make some comment about how can we better design the new superalloy with better crack susceptibility, so avoidance. And then summary and conclude the work. So, I mean, just to remind you this slide again, that our argument is that we need new material for new process. That is the key message, because the existing superalloy or existing nickel-based superalloy are generally difficult to print, even 718. I will show you in the next slide why. And we usually try to refer to CM247 because this is a material introduced in 1928, which is optimized for directional solidification. Directional solidification used a lot in aerospace industry because they have a high volume fraction of gamma prime, 65% to a bit above, so 65% in nominal composition. 718 is actually older material, back in 1965, but this material is very superior in the sense that they use a lot in aerospace industry. No one can replace this yet. So in the state, trying to looking at pre-printing of 625, right, with a similar composition, but that is a study there. But this is a raw material. And then this is the tool we want to focus on. So you will see CM247, or we have another one which is directional certified as well, Inconel 939. But anyway, this 718 and 247 here has been used to print. But as I said, this is actually optimized for this raw hot working and directional certification. So do we need a new material that may be better for new process that we said, additive manufacturing? So we are now probably in the Renaissance period of additive now. It's become going quickly and probably going plateau in about next 10 years or so. Probably it's saturated at some time. So we need to rapidly find a way to produce this. I mean, and then we can move the technology forward. So in terms of alloy by design, this is not inclusive in the sense, just illustrate the concept that we design this because the alloy design basically to rank the composition that actually give the property that we want. That is the principle, right? You want to have whether or not precipitate strengthening. That means the particular element will contribute to that significantly. Or if you want to have chromium and aluminum, this is mainly for oxidation resistance. Or if you want to have a long-term stability, ruthenium will give you that. And but the most important thing for superalloy is actually high temperature property in various strengthening mechanism that you have. If you talk about aluminum, titanium, tantalum, this is actually gamma prime forming element. and this will actually going to be gamma prime after or secondary phase. So nickel-based superalloy is a two-phase material, which is gamma and gamma prime. You can think of as a composite if you are working in composite area. And this gamma is actually softer phase than gamma prime. It's like kind of fiber, a carbon fiber composite. So we give strength to the material. But in this, the nature is quite surprised because I didn't have microstructure here. I just say verbally. These gamma prime, actually the way they form in the homogenized condition, they form in a cuboidal structure. It's so surprisingly due to the crystallographic orientation and some crystallographic relationship. I mean, this is in the L12 phase compared with the FCC. So FCC L12. So and this one is, if it's going to be the grain boundary strengthening, you may heard about using boron to decorate the grain boundary to keep the strengthening. So this is another grain boundary strengthening mechanism that we can induce to the material. Or if you talk about solid solution, it's actually refractory metal, including carbon, chromium as well. We give the refractory solid solution effect to the material. So this is how this is about 10-15 elements that we use for nickel-based superalloy. Combination of this, I mean, believe me or not, nickel-based superalloy is a multi-component alloy system from 10 to 15 elements. So that will give you super property like high temperature resistant and also a high temperature, degradation, mechanical, chemical degradation that resists to that high temperature mechanical and chemical degradation. So process by design. Previously, now we talk about composition. So I'm saying this as alloy. So there is nothing about process. Alloy is alloy. Composition is composition. But when you process it, it's probably different because when you process it, it's actually, for example, this is a very old work in 2000, 2001. They call numerical study by David Dye at Imperial now, but he worked his PhD at the University of Cambridge on the weldability of Inconel 718 superalloy. I believe if you are in Inconel 718 research, you will know this paper very well, that even you call this alloy is actually weldable or printable, but actually the working area or working or sweet spot is quite small. If you're talking about carbide liquation here, I mean not fully penetration, porosity formation, grain boundary, and then solidification cracking. This is a working condition only for this Inconel 718 with, under condition investigated here, definitely this is for welding. So they didn't do anything at that time. So they identify this defect and plot the diagram. And you will see that it's quite complex, even something we call printable material. So we have to notice that this is actually stannate cracking and stannate cracks susceptibility is used as a weldability indicator. So this is what is happened here. So based on the understanding of the gamma prime fraction, they believe that there's something related to gamma prime forming element, which is aluminum and titanium. And then they try to map this composition onto this they call weldability diagram and believe that based on empirical study, I think that back in actually 1940 or something like that, there's a paper in US and try to identify, okay, this material is actually not printable, not weldable that time, and then this one is printable, but it's actually indicated by the green color here. This is actually weldable or printable material for nickel-based superalloy, existing nickel-based superalloy. So this is when you gamma prime increasing here, they believe, but I'm quite interested in this diagram because there's no gamma prime during 3D printing. right? In powder, have you observed gamma prime? No. But in this case, probably relevant, yes. But I don't know why people still keep citing this paper, because in welding, you have the parent material. Parent material is a fully homogenized structure when you weld it, right? And then that means in that material contains some gamma prime after homogenization. So gamma prime is relevant, but why? This is my speculation and also question. Why in AM people still referring to this diagram, even we don't have gamma prime at the starting condition? This is my first question, actually, when I was a lot younger than this, and this is inspired me to dig out more. Why? There's no gamma prime. Why you link this? And this is purely based on empirical study on a particular set of material at that time. So again, there's some other people proposing this diagram again, but they later looking at more combination of gamma prime plus another phases, and then trying to say that, okay, again, this based on the experience, observation from experiment or whatsoever, and try to link that there is some ready weldable material in this zone, but again, not completely, because some zone is mixed up with the red and the blue dot here. So that's very weldable. Don't know what does it mean as well, and then difficult to weld. So or very difficult to print. Again, it's also linked to this forming element again. Again, if you say, that's why I carefully choose the word, this is a weldability. There is not AMability, because again, it's about the forming element, not gamma prime per se. That's his inspiration. That's why we believe we need the new way to understand this. So what we did, you can scan QR code here. That will bring you to the paper that's going to present here. But this is something elaborate more next lecture, because this is more about data driven as well. We screen ranking and then do a lot of calculation based on the existing nickel-based steroid database. And then what we did is actually we used the two indices here. I think I repeat it again. One is actually strain rate cracking Merlin indexes. Again, this is linked to the gamma prime fraction, but we add niobium and tantalum, which is small fraction, and then we say this is the indices. If you vary the content of aluminum by 0.01 weight percent, and then you will get the combination of the material. Let's say this one varies 0.01, and then another one 0.01, or keep it constant, vary 0.01. What you will get is that you will get about 10 million composition here in the range of the acceptable nickel-based superalloy, not too much. So because you have a range for each composition already for superalloy, and then you can get we call design space here that you can looking at in the gray dot, and you identify the range that you believe this is a working condition for additive manufacturing, and then they kind of draw this line and get the window of the fishing range. As I said before, fishing range should not be 400 like CM247. I mean, this is also 350 as well. We set it below is about 300 or 280 something for both composition, and then we select these two as function of freezing range, and it's actually not too high in the cracking index. So one is actually very minimum in crack, I mean, based on this index, and another one a little bit acceptable or at the border. So that's what we call ABD 850, which this material perform well at 850 degrees centigrade and 900 degrees centigrade. So we call ABD 900. And then we print this one out, and what we've seen previously, that is actually minimum crack of crack-free in printing condition. And then you will see that the texture is not very heavily textured material as well. So we believe we need to looking more why this happened like that. I mean, it's combined. Now we better understand based on this one. I mean, this is a 60-50 years ago. They proposed we better design this one using more knowledge-based methodology. Someone asked me what we use. You can look at some patent that I will show a reference next lecture, last one, that you can find more information from that. Or the paper, the first paper in 2009, talking about number of empirical equation we use to feed in to the alloy design code, and also a thermodynamic calculation in the background. And yeah, this is what we got. And the question now is that why this is print better than this one? Why this one print better than the existing one under the condition investigated? This is the next inspiration. And this one, actually ABD 900, is not actually speculation that's print good, but we already, not me, but I mean the company, the spin-out company from University of Oxford, previously called Oxmed Technology or Alloy Company, they actually successfully, commercialized this ABD 900 and use this in the rocket engine kind of to print a thin wall structure using laser powder-based system. Has been tested. I think it's not actually new. It's quite old. It's 3-4 years ago. It's there. It's used. And after we published, just right after that at the same time. So why this working? Why it's not? The previous one doesn't work. What is the crack susceptibility? That is the motivation of the work here. So what we do, we said we try to use the computational framework to link this process, structure, and property relation, especially microstructure, and try to understand why it's happened like that. And then from the aspect of microsegregation, elemental profile, and solute trapping, we believe that may link to the crack susceptibility. That is what our hypothesis. And then what we do, we actually simulate this Melpool simulation of 3 nickel-based superalloy and try to link this to the property prediction later. So based on this, we talk about alloy design, we talk about process design. We want to actually design from microstructure design as well. So we link composition process to microstructure development. So the composition of the microstructure and control here has been very important in rapid heating solidification process, like I said before, because in this binary system, nickel titanium, you will see that it's not homogeneous. It's actually heterogeneous, solidification. You will see some distribution of the nickel and titanium separately, and that means there will be some grain which is formed inside the Melpool before surrounding with liquid, so equax may form something like that. So this is inside that we provide understanding from nickel titanium system here based on simple binary system. So it inspires us to look at this in nickel-based superalloy, which is multi-component system. Another impact on this microstructure design is actually about composition change induced by the process, because our previous work noticed that there is some change in the composition, especially the high vapor pressure element like chromium, and then even nickel itself also prone to vaporization as well. So the collaboration with Professor De Broglie and Dr. Mukichi at in US, we can actually get some predictive capability of the composition change doing the 3D printing of these 4 nickel-based superalloy. I think that is relevant to the context in the previous slide that I mentioned. We will try to understand more why this one is actually not non-printable. So at Queen Mary University of London, in my research group, we are having the 3 frameworks. So we do Melpool simulation, as I said, in what you've seen yesterday as well in the lab session. And then we do solidification, liquid-solid transition here. And probably you can implement some solid-solid transformation framework here to understand the phase formation. Again, this is subject to the rapid solidification. I will give you some example of 2 material systems before we go into the main content of superalloy. The first one is titanium 64. So this is one of the important material that you use for implant application as well. So you will see that even this is the tertiary system, Ti 64, is still complicated enough that if you follow this dashed line, when you become liquid here, it's liquid here, and then if you cool down the temperature up to solidus temperature, 933 Kelvin, and you trap into this, liquid beta grain zone. It's a bit mushy zone before you reach to the solidus temperature at 1978. And this is the beta grain, which is BCC in nature form. And once you reach to this about 1269 Kelvin, the beta transformation temperature is transformed from beta to martensite, and then after that go to lab martensitic structure. So how this actually transform is important, because in titanium 64, the spacing of the lab is so important for the final property. So we want to see how can we predict it under the condition of 3D printing. And this is what we introduced the framework. The paper just published very recently, not I think 1 month or less than a month ago. But what we do, we first predict the pi beta grain. So what we see is a pi beta grain, and then after that you need to impose the phase transformation from here. Just this point is so complicated. To transform it to be alpha and articular phases, martensite here, and you can get an idea how this microstructure evolution. And this is actually happen in real life. We simplify this diagram to be about it. So you will see that this is, if you're interested in this, if you do some kind of diffusion-driven problem, this if it's followed as normal, it will be like this in forging of the titanium 64. But if it's rapidly cooled, the phase which is formed will be alpha plus alpha prime. So it is so complicated now, because the martensite here is so important. How can we understand is how it's formed, and how can we avoid that? And what we do a 3-layer deposition under the direct energy deposition process. And we try to get pi beta grain, first of all, and then we predicted the transformation at different location of the build here. And then you will see, you can get some feature. It's very fine calculation here under collaboration with Beijing University of Technology. So compare with TM with the triangle, that you can see the feature the same in the simulation. So basically what we compare is actually we compare the whole figure from experiment and the simulation. This is what this kind of simulation can provide you. And we believe this model can be beneficial for changing the process condition later. That is the idea. But the framework here is a mathematical framework, quite complicated, that you need to link with a computational approach. This is the, an example that want to show that why this so important. And then if we can understand that, we may be able to understand how can we reduce a crack susceptibility as well. Again, but titanium is so complex. I'm not saying nickel is easier, but what I want to just bring your attention is that different material system, if you come to ask me, you're talking about aluminum, copper, nickel-based superalloy, I would need to ask you which nickel-based superalloy you're talking about. It's going to be gamma prime or gamma double prime delta, or it's so many variety of nickel-based superalloy in the metallurgy point of view that will make it differently in terms of solid mechanics. Or if it's solid solution nickel-based superalloy, is also another story. So it's, as you know, from mechanical engineering. But nickel-based superalloy, that what we're talking about, is mostly gamma prime strengthening superalloy. So our inspiration to do the simulation in the microstructure detail in nickel-based superalloy, because as you see in the build along build direction and transfer direction, it has different microstructure clearly, from columnar grains to equax grain, and this is with the cellular structure. along the build direction, you may get this kind of melt pool and feature at its time scale and as its length scale. And the cellular dendritic structure here is a micro to nano, in the micro nano scale here, induced by ultra high heating and cooling during LPBF. And the in situ observation of this phenomenon, especially solute transport and microstructural evolution, is very limited. I think I would say almost none or no such observation, because the resolution of this is quite small. And the high fidelity simulation will be relevant to rationalize this, what happened in terms of laser matter interaction, heat mass transport, and subgrain scale. We're talking about in the 10⁻⁶ to minus a micro or about 100 nanometer scale. This solute partitioning between cellular or dendritic trunk and intercellular or interdendritic region will contribute to the non-equilibrium rapid sulfication nature. So we'll be study this solute trapping or solute transport in subgain scale and try to understand the non-equilibrium during or after rapid sulfication. So what we do, we suspect that why the new design superalloy is crack free. So we try to observe using first X-ray synchrotron image diffraction in light source at Harwell in Oxford, and combination with atom probe tomography in as printed condition, combined with the high resolution scanning electron microscope or STEM. And then we do the secondary iron mass spectroscopy to understand the oxide at the aspirated condition for these two alloys. And then you will see that there is no gamma pump peak present detected by high energy light source like synchrotron at all. And its print solid solution, actually you will see here, is a perfect solid solution material after printing. And atom probe also shows some, I mean, there is some segregation, but it's not actually heavy segregation. If we do it at different, if we do post treatment and at different, subsolvers or supersolvers, you can actually segregate out or homogenize out some structure. And then this is quite solid solution. If you see profile here, yeah, there's something across the boundary a little bit. But this is what we got, and then we know that, okay, this different from existing alloy. So now, what happened to the crack sample? What happened to the crack sample? The crack sample, actually, we identify this crack propagation that we said due to the ductility dip here. And you will see that there is a zone that trap, and probably they change the microstructure a little bit from columnar to kind of equax. And then this is a black, dark shade like zone. And then we try to make a kind of hypothesis what happened here, why it's actually stopped here, rather than penetrate through this crack. And this is another curiosity that we do. And then we know that the crack greatly accelerate the rupture of superalloy in high temperature condition. And this segregation basically determine the liquid film formed during solidification, the solute segregation and liquefaction in a heat affected zone. Something that remain unknown is that how this solute transport element are transferred during non-equilibrium rapid and repeat thermal cycle. And because we don't know why it's actually trapped at the bottom of the melt pool. This is the question we ask ourselves, and then insight into this transport will be actually provide a better understanding what actually hopefully going to eliminate crack defect, because if we know this has an impact on the crack propagation, we can do something to mitigate that. And then that's what we are trying to do too. We believe this will be a key understanding of solute transport here will be key for the additive manufacturing processability. So what we do first, we ran a model to understand, this is the real simulation in 718. So we will tell you later that I will tell you later that we calibrate against the small scale, I mean, how to say, micro or nano length scale experiment as well. So we calibrate this before we predict the solute segregation profile. Especially for incandescent 1.8, we chose niobium segregation profile because this is a detrimental phase that's present. So what we do, I think I don't need to repeat this, is in the very first slide. And then you will see that we can predict niobium distribution in the incandescent 1.8 here. And it's actually real that it's happened at the boundary. But we not quite understand yet. This is just quite a big level, big scale model. Next thing we want to do, we try to solve this big equation here and incorporating the solute transport as well in the multi-component system. So that means at the different nickel-based superalloy, you do a pairwise calculation for each system coupled with thermodynamic data available that you can actually extract the solute concentration, these partition coefficients that I will talk a little bit more about K later, linked with the process condition like platelet number like later. And then you use this understanding to develop understanding how the microstructure evolved. And this solute concentration is actually in the range of the concentration here, partition to C0 to C0 divided by by K here. And then this is the, we call segregation indexes. So if this one, if it's less than 0, will fall into this one. If more than this, it fall into this one. And then we identify the segregation profile specifically for CM247 based on our understanding in the experiment is a hafnium at the segregated in the grain boundary, and the niobium for the lava space, which is decorated at the grain boundary as well. So we focus on these two, but there is some other reason why we focus on these two profiles from metallurgy point of view later. And then interestingly, because the new superalloy actually solid solution, so we use the avalanche segregation index for the new superalloy. So that is equivalent, or what is it called, equivalent segregation index. So it's an avalanche profile. So what happened, we will see now. So the reason why we chose these three, because this is a composition studied here. So we have hard to print, gamma prime strengthening hard to print alloy. Yeah, we have incandescent 1.8. Supposed to be easy to print, but this is gamma double prime strengthening alloy. We have intermediate gamma prime strengthening alloy designed for AM here, which is a new composition. This is the three material that we are studying here. And then you focusing on this one, hafnium. It has only 1.3% weight percent, but instead of niobium, it's 5% here. And this is what we found. And then this is a verification of model using 718. What we did, we define a calculation domain here, identify between the multi-phase solver. So that's what you've seen before, nothing fancy. But what we got here is actually dendritic. If you remember yesterday, Hong Hao present, this is what we can predict. But this is it's a 3D, but a thin slab of 3D, represented by the fluid flow in the 3D model. And then you see, this is prediction, not experiment. The predicted structure here, in terms of dendrite arm spacing, is so similar to the male pool in the experiment. And when we look closer to this is a primary dendrite, you will see this is the spacing of that is in the 1 micron scale. And we use this one to validate against the wavelength dispersive spectrometer in the electron probe microanalyzer APMA here. And you want to validate or verify your model with this segregation profile across this one, and then experimental and simulation. So to make sure that your model is actually predictive enough to do something further. And this is only niobium profile. And after that, you're looking at different location of the male pool and try to extract some avalanche dendrite arm spacing at different level, because this is the spacing that segregation profile taking place. So a summary of this is niobium concentration distribution is across the cellular structure, cellular trunk here, and intercellular area. That's why I said micro segregation linked to the dislocation. That is the next study actually. So segregation length here is an oscillation of the solute profile is increased and decreased because of refinement of the cell structure during the high solidification. And this simulation result has been verified with experiment in terms of the solute trapping. So we can approximately capture the effect. And what we do now, we try to use this for a particular cases. So this is what happened in a multi-track, multi-layer deposition. So we start with the avalanche segregation profile. You will see this is some layer adding up. And then what you see here is about, this is a thermosoluto fluid flow that actually doing rapid solidification of two-layer deposition here. And I want to highlight here in the avalanche composition here that the solute actually enrich here once the second laser attached. In the first layer, you leave behind enriched solute zone and the solute dilute zone, and this actually, as for solidification progress, the cellular structure actually taking place. This is a panna growth because we're talking about high cooling rate, right? Panna and cellular structure will form, and after that, once this one progress, the solute enriched zone actually going up and is leave behind the solute dilute zone. And after that, the cross structure, due to the fluid flow as well, it will give this cross structure. And you get the severe segregation profile here. After that, once another heat actually put it in, before, this is the first track, right? First track. The second one, there in overlap zone, the heat input here will push away this solute because it will be remelt again. And then this zone has been remelted. And then this is sufficient solute mixing. It's mixed together. And then this leave behind the solute dilute, so there is no heavy segregation at this one. So the panna growth actually proceeding to grow this way. And the cellular structure actually become penetrated here. This make this one enriched. So you will see that enrichment of the solute actually related to cellular growth here. And then you get that this is improved solute distribution. That means if you print it more and more, the solute will, but still, some cases without care, you will trap some solute, and that's what we call solute trapping. What we see, what does it mean by that? If you see here, this is melt pool, you see with the porosity as well. In CM247, if we move a little bit to the highly segregated kind of material like CM247, we talk about hafnium profile. Again, this is coming from expert modeling only. So you will see this is substrate layer and then second layer here. And then the metal here is actually, this is a melt pool, heat affected zone, solidification progress here, and this is still in liquid here. So you can identify based on the gamma prime forming element. Again, this is not gamma prime yet. It's just a forming element. There are preferential segregation of some element based on the calculation here, that in the isotherm of the solidus temperature of this melt pool, you will see that there will be some in the liquid and in the solid. That's what we call dilute or enrich. It's based on quantitative measurement here. So previous slide, that's what we do. So we will see that in the liquid, this actually dilute or otherwise enriched zone. So that's one. We cooperate because we believe this is in the eutectic zone here, nominal composition here, but you actually trap into the rapid solidification zone, that actually move a little bit that MSE and MSL here to be closer. So that's why, I mean, this is something doing with this phase diagram systematically. And then you will see the strong inhomogeneity of the process here lead to what we call quasi-solute trapping. So when you get strong inhomogeneity here, in the second layer, that will trap a zone like this. I think if you go back to your sample, I bet that you will see this kind of thing as well. Most of the time, that's what we'll observe across the sample. It's not things speculation, but I think there's something doing with the process. So that's why. So we try to relate now. So now, what is the use of this? At the end of the day, I ask myself, what is the use of this one? Actually, when we know hafnium profile here, you'll see some highly segregated profile compared with the 718, which is actually quite good segregation profile, but still you have some segregation. But whereas these, sorry, I mean, this is CM247 is highly segregated. You will see a lot of hafnium present everywhere, consistent with what we've seen in the experiment. And then in concern is kind of intermediate, but this one is not really segregated a lot, but it's quite of average. So that's why you see this kind of zone as well. This is a zone that you see, which is we call solute dilute zone, right? It's trapped in the melt pool, and this is due to because we believe effect of the melt convection during the printing make it actually, let's say if you if you decrease the cooling rate here, let's say this is the solid liquid interface, and once the convection, if you have the convection flow, this will actually it will actually increase this zone. So convection will suppress this, but so strong flow will going up here, and this solute trapping induced suppression will be impact on the niobium concentration. It will be from strong to suppress this zone, and that's actually the promotion of this convection actually give rise to the increase in the I think this is the increase to the undercooling temperature of the crystal growth. So if there's sufficient convection, it will increase the undercooling, and the partition coefficient, which is K, will be increasing. So this gap here will lead to difference in the partition coefficient during processing. And that is what it is here, the variation of partition coefficient when you have, this is partition coefficient K, and then this is the platelet number, which is linked between the crystal growth of the process. There is a interfacial velocity of the growth, interfacial width, and the solute diffusivity in liquid. And then if you use this as an index, you will see that means if you have the larger platelet number, that means you probably promote more interfacial velocity. The melt pool is travel faster. So that means if you quickly, bang a lot of energy into your system, you will fall into something called solute trapping zone. That means it's not equilibrium anymore. It's going to non-equilibrium. And this is actually the blue one related to your, this is not your scan velocity, no. This is due to the scan velocity or energy is contribute to the velocity in the liquid. And this diffusivity here will promote this zone. So you get trapped in this zone. Or it is a freezing length coefficient, because if you have very rapid certification, this one will actually promote or change your freezing length as well under printing. So it changes based upon this equation. So your moving interface or liquid here, it will change based on your partition coefficient here. And that actually, the magnitude of this identify something we call characteristic solute trapping velocity. And if this absolute or interfacial velocity actually very high, in the range here, 0.121 here, intercellular segregation will taking place, especially the partition coefficient such as hafnium and carbon that's far from 1. So that means it will trap into this zone. And then if you're talking about in near equilibrium 1, if you high solidification rate as well, if you are in this zone, it's still trapping as well. Your freezing length will change. So it will be decreasing. So such as the solute profile that contribute to this, such as zirconium and copper. So what is mean here is that the process parameter is so important that we know in CM247 LC. If you change your hash spacing, power, energy, you will actually get to different crack density based on the previous study here in the LPBF. You will see if you use lower density, your linear energy density even higher, but your crack occurrence is actually lower. But in the case of CM486 here, it just shows similar composition here. And this one contribute to the energy density that contribute to the interfacial velocity that talked previously. But that means this is suggestion now. The influence of the common element in superalloy on crack susceptibility. I mean, this can be found in the Nature Comp paper if you like online. So the freezing length here will be varied as well based on the process parameter you use. Surprisingly, that means we cannot control like casting. We know the freezing length, so dynamic the process. Second, segregation length. If you see in the yellow exclamation mark dot here, that means the composition that we need to take care of a little bit more in terms of solute trapping, because hafnium, zirconium, and copper actually contribute to the crack susceptibility as well. The graph to solute trapping here, so this one is okay. Freezing length, hafnium also contribute to segregation length and also freezing length as well. So this is the new crack susceptibility that we identify based on the insight from the model. We believe that in the alloy design of superalloy, new superalloy, if they have different solidification behavior of superalloy, will be easier to reach the solute trapping if strongly partitioned solute element were removed. So that means if we can remove all this, but probably it's not good for this hafnium because this is a grain boundary strengthening element. Not sure. Or people trying to see the role of carbon as well. And the larger segregation length mean the wider gap of solute trapping you will get. That means hafnium you have a lot in the CM247. This will be detrimental to the crack susceptibility. Sometimes, I mean, it would be more challenging to reduce and complete elimination crack, but it's about control and optimize process parameter as shown before that may help, but not a lot. It's about what is the acceptable range of the crack, but probably we cannot compromise with crack, right? In the flying component, it's probably not possible. But this kind of insight, I mean, you see now, I'm really trying to link process with composition, with microstructure, and now trying to say about property. So this all the, I mean, PSP is a way, the motto for our research, that we try to show that this model can give extra information. It's really extra more information that you can get. And this is these two, apart from freezing length, we add one more from the previous design alloy. We add segregation length as well. So if you map this across, representative nickel-based superalloy, based on the understanding that we said previously on the lower length scale model, we can see that the green one represents something that the length that we can print, but the cross dot here is, I mean, this is a processing window, and this is the cross here is indicate the not hard to print alloy. You will see that most of the time they have very high grain boundary segregation, a strengthening element and primary element for gamma prime. This is systematic investigation now, but it's not all the time that you have some percentage of gamma prime and you cannot print them. You see that mean what is said here is mean that not only one parameter can say to you. It's sometimes controversial because some high gamma prime, some of them can be printable or processing window is wider. So high gamma prime like CM247 or incandescent 308 LC is considered unprintable with crack, but even higher like Rayne 77 is crack free based on the literature. Definitely it's probably not the same condition, but this is what we found. It's a bit controversial as well, but I mean that's one of the things that we make an argument in the paper. And higher hafnium plus zirconium here will be hard to print, and this related as well with the high gamma prime phases, nickel-based superalloy. So elemental segregation worsen the printability of precipitate hardening superalloy, and as well this will sensitive to the cyclic thermal stress. And the crack may be eliminated in the hafnium-free CM247. Again, this is, we made some suggestion. Whether if we totally remove hafnium, we can print it better. I think you may know some study talking about the variation of hafnium in the CM247 as well. So we believe high gamma prime nickel-based super with less grain boundary strengthening element will be the ideal solution. So the suggestion is that strong tendency of solute segregation in cellular trunk and intercellular region will further impact the solidus temperature. So as we said before, the fissing length is changed, and changes will change the solidus temperature as well. So elements such hafnium and zirconium are strongly recommended to avoid. So we want to remove if possible. Whether or not it's possible is another question. So in kind of summaries, I just want to say that the fully coupled thermofluid soluto microstructural mathematical model is developed to understand dynamic solute transport and element segregation in AM. So we revealed that the non-equilibrium nature of intercellular solute segregation and cellular structure here occur at the subgrain scale in the multi-track, multi-layer fusion and solidification of LPBF. And the prediction of the melt-pool solute trapping zone microstructure are verified by the reported available conducted experiment. So we have used both literature and also new set of experiment. The role of this melt convection on the elemental segregation is proposed as a mechanism to form the solute trapping region and microstructural evolution. Hard to print superalloy can be additively manufactured without removing essential minor element by further accelerating the solidification to promote the solute trapping and hence reduce intercellular solute segregation. Qualitative estimate of the crack susceptibility in terms of the processing window is developed. I think I showed you before. And I hope this will aid the alloy design of superalloy for the future. So we hope this modeling framework can be powerful too. So this modeling framework we're talking about is more multi-physics, multi-scale simulation here will be useful for further develop other study like this one will be useful when you want to do or design a new alloy in additive, especially in the case of blend elemental powder. So we call in situ alloying. You alloy A and B, it will be AB or ABC with AB, which a lot of study, especially in the high entropy alloy community. They mix 4 or 5 together and blend it under the beam. So this is probably a way forward and give more opportunity rather than going to do atomization all the time. But anyway, this is some kind of further work, and hopefully this can be beneficial for elemental powder in high entropy or performance steel as well, which you have less number of elements present in your process. But again, this is just outlook from this work. And I hope this one is a showcase for multi-scale, multi-physics to really bring bridge the scale from low length scale to the impact on the industrial scale usage for alloy design. Again, this kind of understanding will be fed into the alloy design algorithm for data-driven, for example, and that will be the last lecture tomorrow. Thank you very much. And are there any questions, please? Yes, sure.
In one of your slides, you have shown the new alloy that you made based on merit of strain edge cracking.
Based on
Merit of that SAC. That strain edge cracking index.
yes, strain
Yes,
edge cracking.
Yes, sir. Can you go
But
to that?
that is the early inspiration of this work.
Yes, sir. So,
You ask something about tomorrow again. Okay. I know what this one. Yeah.
so this is the previous one.
Previous one.
Means where the micrographs are showing reduced cracks. No cracks in the new alloy, cracking in Inconel 718.
I think that's
Here.
this one.
Yes, sir. Here.
Okay.
So the micrographs are showing hot cracking, and the index is strain edge cracking.
No, be careful. I already said it's so many cracks actually acting on this. You can see more in this ACTA paper how many crack mechanism operated. But what is your question?
So in the micrographs, they are solidification cracking. In the micrographs,
Mixture, no. It will be ductility dip, liquation, lack of fusion. I mean, the crack here, it's hard to identify because based on imaging, we will say the crack in this sense means any line in the microstructure. We not classify yet because the one here is image-based analysis. It's not like tomography that we can identify the feature like the previous work. That makes sense. This is just about MSc, PhD. I mean, this is the same one I showed you previous talk, but this is just inspiration. So
okay.
I just want you to be careful that this is just a way to quantify the defect content in the printing, but we call this crack susceptibility. We call all these are crack, but this feature, including this may be liquation, solidification, including something of porosity as well, because it will, once we do the different contrast in the image, this will bring up. We will not remove any feature, but that means you need to have a criteria to remove it, but not yet. We didn't implement anything because how can we make sure we select the right? But this defect in this vicinity will be captured and then analyzed. So what you may say is actually, if you remember my talk last one, you will see the distribution. The smaller parts probably related to some defect. The bigger side with the lengthy one may be cracked. I don't know, but this is something we need to do further analysis. Does this make sense?
But those cracks will not be SAC cracks because they are as fabricated. Those samples are as fabricated. There cannot be strain edge cracks. Correct, sir? Because
you're right, but if your print is quite high, at below you have intrinsic heat treatment.
But no gamma prime was reported. You are saying that in
yes, but that is why I mentioned that this has to be improved into the alloy design, because this is not, they make assumption the same as they have gamma prime, But actually, no. But this is the best assumption at that time, back in 20, I think 15, 16, that they first done. So this understanding that I show you later is not yet available. So you need to consider the timeline as well. So this is a huge amount of data and effort to make it, because this one based on the alloy design in the disc and turbine blade. Yeah. I know what you mean, but that's why I said no gamma prime Y matter here. But anyway, this is the best approximation that time. Model just a representation of reality. We cannot expect 100% accuracy, but we need to use with caution. We need to know the condition, what is working. Yeah, I think. Thank you. Any other question?
Sir, I have one more question. Like, let's say I print a big turbine blade. Let's say a big turbine blade. From top to bottom, the segregation profile will vary. Let's say in top there will be more segregation, in bottom there can be less segregation.
I think another way around, but anyway.
Sir. So the question is like how to go about the heat treatment procedure, because how to ensure that part throughout is, homogenized, precipitation, volume fraction is uniform from top to bottom. Since we have
I think there's so many things to do. It's not about heat treatment only. It's about the way you fabricate it as well. Because you cannot expect something highly segregated at the bottom, and then you will homogenize throughout. They're probably 30, 50 millimeter up. But later, I think, in my opinion, you need to change your printing strategy, like scanning pattern, try to control different way to get better thermal signal that can homogenize the structure as printed. That's why digital twin may come to a big play in this kind of research. So that's why we need to collect it on time, on fly, yeah. So it doesn't mean after only. It has to be during as well, yeah. Because if you have heterogeneity across the sample, it's probably an easy fix for heat treatment. But if it's highly concentrated, I don't know. The best way is just remove the base. I don't know, yeah. But again, I'm not in that length scale yet. There's my previous postdoc now, academic, he's looking at heat treatment. There will be some interesting heat treatment as well as a following paper for the successful material here that we published in Superalloy, that you can see different heat treatment protocol lead to different microstructure, and hence we identify the liquidization effect during this, as a result of this structure. You can follow, it's actually in 2020, this paper, yeah. But I don't think you can homogenize, but I may be wrong. There may be another way. Yeah, thank you. Any other question? You want to ask?